We're going to review here some algebraic techniques that are going to be important in this unit where you'll be working with similar figures. One is how you solve proportions. A proportion is simply an equation where you have one fraction equal to another, like this one here. And the way we solve a proportion is, you remember, as we cross multiply. If two fractions are equal like this, then we know these numbers multiplied together have to equal these. So that means 4 times 8 is the same as 15 times x. Or 15x is 32. So therefore, if I divide both sides by 15, I get x is 32 over 15. This is a perfectly good answer. If this bothers you, it doesn't reduce because this is only powers of 2 and this is not even. If you don't like that, you can get a calculator out. There's a calculator and ask it what 32 divided by 15 is. 2.13 repeating. So if you prefer, you can say this is 2.13 and the 3's go forever. So here's a slightly trickier example. So again, one fraction equals another. So if I cross multiply, I will get x times x plus 5 equals 2 times 25. So if I multiply this out on the left, or on the right, I get 50. On this side, I get this distributes onto these two terms, and I get x times x, or x squared, plus 5x. This is a quadratic. It's second degree. You will occasionally see these in this unit. Any method we use is going to involve getting everything on one side so it all equals 0. So you can either throw the quadratic formula at this, which you'll have to look up or ask about, or you can factor this. So I'm going to factor this. You've learned different factoring techniques in algebra. I know this one's going to factor. X squared is going to be x times x. I need to get minus 50 when I multiply these numbers here, and by trial and error, or by thinking about it, or by using a box method, I eventually can figure out this is going to have to be x minus 5 times x plus 10. And if I multiply these things together and I get 0, that means either the first factor is 0 or the second factor is 0. So this leads to x can either be 5 or x can be minus 10. If I go back and look and see in the original equation, see if these make sense. X equals 5. If I check that in here, I get 5 over 2 is 25 over 5 plus 5 is 10. And indeed, these fractions are equal. 5 times 10 is the same as 2 times 25. You can see if I multiply this by 5 and this by 5, you'll get the same answer. The other answer was negative 10. If I check negative 10 into the equation, I get negative 10 over 2 equals 25. And then this is negative 10 plus 5, which would be negative 5. And these are also equal. I get negative 5 here, and I get negative 5 here if I divide them. So these answers both check. In this unit, we're likely only going to be interested in the positive answer, because these are going to represent lengths of sides of figures. So the negative length won't make any sense. But if it's just a pure algebra question, both of these answers would be fine. Another type of problem you're going to see is problems dealing with scale factors. So I've got a couple of different scale factor examples I want to do for you here. First, this says a scale drawing of the solar system is labeled 1 inch equals 3 AU. If you've never heard of the unit AU, AU stands for astronomical unit. It's the distance from the Earth to the Sun. The Earth to the Sun is 1 AU. So whether or not you knew this or not, you could do this problem knowing that or not. So here he says Mars is 1.5 AU from the Sun. How many inches is it from the Sun of the drawing? So this means here, knowing the scale factor, and then I have this, I can set up a proportion. I have 1 inch over 3 AU. That's the scale factor of the drawing. And then over here, I'm going to have the particulars for this problem. Okay, Mars is 1.5 AU, so that's going to go down here. This is the AU part of the scale factor. how many inches it from the sun in the drawing. So this will be my unknown. This is going to be an unknown number of inches. If I look at this equation, the AU's are going to cancel. I'm going to have inches up here on top. And then I cross multiply this like any other proportion. So I get 1 times 1.5 inches is 3x. I divide both sides by 3. I get x is 1.5 over 3 inches. And this is exactly 1/2 an inch. So my next example, let's just do it the reverse order. You measure on the map and determine that Neptune is 10 inches from the sun on the map. How many AUs is that? So how many AU is Neptune from the sun? So again, I have my 1 inch to 3 AU scale factor. And now I know Neptune is 10 inches. And I want to know how many AU that is. I could do the cross multiplication here, but I can just look at it and expansion this. If this is 1 and this is 10, these fractions are going to be the same. If this is 3, this has to be 30. I can do this by inspection. So I get here x, this has to be 30 AUs. That's how many AUs Jupiter or Neptune is from the sun. There's another type of scale factor that you might encounter. That's a scale factor like this. A model train has a scale factor of 1 to 87. If the caboose is 4.3 inches long, how long is the actual caboose in feet? So presumably this is the model caboose. You're not going to see a real caboose that's 4.3 inches long. This is a different type of scale factor. This doesn't have any units on it like the previous one where it was inches to AUs. So when you see a scale factor like this, it'll accept any units whatsoever, but the units that go into it are the same as the units come out. So in other words, if you make a fraction with inches on the top, it'll be inches on the bottom. If you make a fraction with feet on the top, it'll be feet on the bottom. So you can use any units you want with a scale factor like this, as long as they are the same. They're going to match. In essence, what this is saying, when you see a scale factor like this is saying that the model train is exactly 1/87th as long in every dimension as the actual train. So let's see how we would set this up. You'll notice here that the model length is given in inches. It's 4.3 inches long. But we want the final answer in feet. That's going to present some conversion issues because this doesn't have inches and feet in it. Just remember, whatever unit you put in is going to be the same as the units that you get out. So let me show you how I set this up. So I have my scale factor 1 to 87. Numbers on the top are going to be the model. Numbers on the bottom, the bigger values, are going to be the actual train. So I know that the model is 4.3 inches long. And I want to know how long the actual caboose is. So since I'm putting inches in here, I know x is going to be in inches also. So if I cross multiply this, I get x equals 87 times 4.3 inches. And my calculator tells me 87 times 4.3, that's 374.1. But this is still in inches because the units I put in is the same as the units I get out when I do a scale factor like this. So now I need to convert this to feet. Now remember, the conversion factor for inches to feet is that 12 inches is the same as 1 foot. So there's my conversion factor. I'm going to multiply by this. The inches will cancel. So I'm going to get 374.1 divided by 12. And over here on the side, I'll use my calculator. And I divide that by 12. I get 31.175 feet.